All right, we are doing an example of a Mclaren series, and it's not the easiest example on top of that. So let's go. I'm going to look at the zeroth derivative, the first derivative, second derivative, third derivative, and we'll see if we need to go further. And I haven't really said much about what to do other than to find the Maclaurin series. Maclaurin means the center of the Taylor series is 0. But first, the zeroth derivative is the function. To prep it for derivative taking, however, got too much stuff over there. Hold on. Moving wires. Okay. To prep this, I'm going to write it as 4 minus x to the 1/2 power so that I can just power through it with the power rule. My exponent is 1/2. Here comes the derivative. 1/2 bleh to the negative 1/2. When I chain rule, I take the baby 4 minus x and I shove it in. But that baby needs to be dealt with and have its derivative taken. The derivative of 4 minus x is negative 1. So I'm going to throw that multiplication of negative 1 out here. And that first derivative is taken. As I go to the second derivative, I'm going to take the negative 1/2 constant multiple and drop it down. And now I'm taking the derivative of just what's in this parentheses to the negative 1/2. And so I start with my exponent is negative 1/2. So I'm going to multiply by negative 1/2 bleh to the subtract 1 from negative 1/2. Give mommy her baby. And then don't forget to multiply by the derivative of the baby, which is negative 1. And then look at the fact that ultimately that gives me 3 negatives. So altogether, a negative constant multiple of 1/4. And that negative constant multiple, I'm dropping down just to make sure to clarify. Nope, nope. That is this. And now derivative taking of this part. So I bring the exponent down, negative 3/2, bleh, to the power of subtract 1 to negative 5/2. Shove the baby in, multiply by derivative of baby, which is negative 1. As I prepare for the fourth derivative, I want to notice that I have 3 negatives, so my constant multiple is a negative number. And it is 1/4 times 3/2 if I ignore the negatives, giving me 3/8. And then I'm ready for the derivative. And I have the exponent negative 5/2, bleh, to the subtract 1 from the exponent. Shove the baby in, multiply by derivative of baby, which is negative 1. And then the process would begin again, but you might be seeing the pattern. Now, without going through the derivative process, but just thinking about what does happen, can you write down what the fifth derivative is going to end up being? if you look at each line every single time, the final simplified answer is negative because you end up with 3 negatives. And then in the fourth derivative, you have in the numerator 3 times 5, and you're about to get a times 7. Still on the constant multiple, the denominator is going to be multiplied by yet another 2. The fourth derivative is already 2 to the 4th power, so this is now going to be 2 to the 5th power. And then the exponent will be negative 9/2. Now, once you figure out the pattern that the derivative itself is taking on, you're probably ready to figure out the pattern for when you plug the center in. When I plug in 0, I get the square root of 4, which is 2. When I look at the first derivative, I have negative 1/2 times. That negative exponent really says 1 over the square root of 4. And thank you guys for helping each other there in chat. When I look at number 2, this constant is negative 1/4. Just this piece. When I plug 0 in right here, that piece is 1 over the square root of 4 cubed in the denominator. And so that's, there we go. For the third derivative, if I take this entire constant, that is negative 3/8. And then this piece is negative exponent 1 over. Denominator of exponent 2 means square root, and I have plugged 0 in, so I'm getting 4 with 4 minus x, but to the 5th power. And then 2 cubed. Wait. I didn't mess that up, did I? Yeah, I'm good. Okay. Then I have the constant multiple over here is negative. Numerator is 3 times 5. Denominator is 2 to the 4th power. And then by plugging 0 in, I get 1 over because of the negative exponent. I plug in 0 and I get 4. Square root of 4 is 2 to the 7th power. Do you think at this point you see the pattern? With n equals 5, it's going to be negative, and the numerator is 3 times 5 times 7, and I'm going to wind up with 2 to what power? Yeah. Let's see, 9 plus 5 is 14, yes. And if you don't see where that 14 comes from, you plug in 0, you get 4, square root is 2, in the denominator, 2 to the 9th power in the denominator, and 2 to the 5th in the denominator, 5 plus 9. Now, once you think you've gotten a hold of the pattern, then it's time to make a formula. And I want you to know that the coming up with the formula part, when it comes to testing, you're only going to see things that you have already seen. And it's not going to be the hardest ones possible out there. So I want you to not feel panicked over, can I come up with a formula and notice the pattern? Also know on the AP test, on the AP test, if you have to find a pattern, it will be a very, very reasonable pattern. It will not be something that you have to think about for a long period of time. You've got an exam that's just over 3 hours long, and one free response problem is supposed to take you 15 minutes. One multiple choice problem is expected to take you either 2 or 3 minutes. And think about how long it could take you to come up with a formula. So realize how much that's going to be on the AP test just based on that information. It's going to be minimal, if there. And it'll be things that are easier patterns to find. This is a harder one. Now, while there is a formula out there for multiplying the first so many odd numbers together, it is way too complicated to concern ourselves with. The textbook doesn't even concern us with it. So for that part, I'm going to say that the nth derivative at the center is negative. And I'm going to start with a 1 because really we did start with a times 1. We just didn't think about it that way. Times 5 times 7 times ... And then we're going all the way up to some number. But we need to find a formula with a pattern to get us to who is the last number there. Then we also have the denominator, and I'll come back to that. In the denominator, we have 2 to the power of something. So once you see that that's what you have, you're now down to needing 2 formulas with an understanding of the pattern that you're using. Now, how do you force an odd number when you are working with these numbers? How do you make a number be odd? And I'm going to start, actually, if you don't see it right away, I'm going to start you off with how do you make a number, How do you cause these numbers to be even? That's where you're always going to start if you are looking at a pattern of only the odd numbers. Once you get a pattern of even numbers, from there you just need to figure out how to go from these numbers to the numbers you're actually dealing with. That could mean that you need the pattern 2n plus 1, or it could mean you need 2n minus 1, or it could mean you need 2n plus 3, or 2n minus 3, and I could go on and on and on. But basically 2 times n plus or minus an odd number. And once you realize that that is the formula that's going to get you to odd numbers only, you now have that in your pocket ready to use anytime you need it. Now let's take a look at the numbers. And I'm trying to come up with a formula for this spot. So what I really want to look at is for these n numbers, I'm going to use green. For these numbers, I'm trying to turn a 5 into a 7. I'm trying to turn a 4 into a 5. I'm trying to turn a 3 into a 3. And I always find it easiest to look at where I'm currently situated. I found what I had at 5. It's going to more easily show me the formula. If I double these numbers, I get all of these. But what I want to get, I want when I use 5 for my n to get the number 7. When I use 4 for my n, I want to get the number 5. There could be some issues with going further in. I'm going to leave it right there for the moment. So now, if you look at the double number, instead of looking at the single number, look at the double number. What does it take to move each of those doubles to the number we need? And I see you've got it. So this is 2n minus 3. Now I've got to figure out how to get the exponent in the denominator. So I'm going to kind of start this list again. I want to be able to, with 5, get 14. With 4, get 11. When n is 3, I want to get 8. And let's just look at those. Also, it helps to come up with the formula if you look at what creates it. So you've got to figure out what's going to work. And we've got an idea typed in. And one thing to notice is that I'm only going up by 2. Wait, hold on. Sorry, I'm looking at the wrong set of numbers there. Whoopsie. Let me try and get that out of the way. Okay. To go from 8 to 11, I add 3. To go from 11 to 14, I add 3. If I go back a little bit farther, I can see, yes. If I am only adding the same number to get from one to the next, then I'm looking at a linear pattern. Linear pattern means a linear equation, a line equation. You might think of it as mx plus b, or maybe ax plus b. But in this case, the variable's n, so an plus b. And then with a little bit of work, you can play around with it and then simplify and finally get to the point of, is 3n minus 1 going to work? Yes, yes, yes. Woohoo! So I finally have a formula for that denominator, 3n minus 1. Now, if you are coming up with a full-blown Maclaurin formula, that is going into a piece of another formula. So what is that Mclaren formula? A function is equal to the nth derivative at 0 divided by n factorial times x minus the center, but the center is 0, so just x to the n power. And you are taking all of this and substituting it in right here. And it may look awful, but it's a formula. However, the formula may not work for the very beginning n values, and that's something to consider. If that happens, all you have to do is take out a first couple of terms, if those first couple of terms defy the pattern. For example, with this one, when n is equal to 0, I'm getting just f of 0, right? So if I look at the first few terms of the polynomial, regardless of the particulars, you're getting the function value at 0 plus the first derivative at 0 times x plus the second derivative at 0 over 2 factorial times x squared. Now, to check to see, does it actually follow the formula, you can look at, if I plug 0 into these n's, does it give me, will I wind up getting something that makes sense? And this says no. This says we've got an issue. If I plug in n equals 1 into this formula, I will still end up with a negative number, which is going to be problematic. I cannot use this formula for those first two, but I can start it when n is equal to 2. So what I can do is f of 0 is 2. The first derivative at 0 is negative 1/4. So 2, negative 1/4. And I'm just overemphasizing the formula. Doot, doo-doo-doot, doo-doo-doo, doo-doo-doo. And then I have this plus sign. And now the formula can really begin, but I'm not starting at n equals 0. I had to take the first couple of terms out of this because they weren't going to follow the formula. N equals 0, 1, and we're starting at 2. And now I'm just going to write it as a messy looking formula. Messy looking formula is, I have this highlight, and I'm going to put where that highlight is negative 1 times 3 times 5 times ... times 2n minus 3 over 2 to the power of, parentheses, 3n minus 1. That replaces the highlighted nth derivative at 0. And I'm looking right here at this formula, and I'm now completing over n factorial times x to the n. Again, it is a pretty messy looking formula at this point. You can, however, move the numerator's denominator to the denominator, so it's not as messy. And so the best way you can write that Yay! I think it's important that when I'm taking you through an example, I give you something that's nice and hard. When you're going to be on your own, if you have to come up with formulas, this is the worst you're going to see. So that is the example. Now, on to what do we need to do today? Today we need to come up with 2 formulas. I want to find the Maclaurin series for the particular function e to the x. And then I'm going to find the Maclaurin series for sine, but we're going to start with the nice easy one. You're going to love this. You're going to love this one, really, really. Here we go. The Mclaren Series formula, I'm going to rewrite it again. Sigma n equals 0 to infinity. That's why you're going to love it. The nth derivative at 0 over n factorial times x to the n power. So the zeroth derivative is the function e to the x. Its derivative is e to the x. And the derivative of e to the x is e to the x. And the derivative of that is e to the x. Therefore, the nth derivative is going to be e to the x. What do I get when I plug 0 in? 1. All the way down. That means that the Mclaren series for e to the x is simply replace that with a 1. And if you replace that with a 1, then it is typically written with the x to the n power in the numerator. And that's actually a pretty decent formula to try to remember. And remember, you will. X to the n divided by n factorial. I want to write out a few terms because you need to be ready when you take an actual test on this. You need to be ready with, I know the formula and I know the first few terms. I'm laughing at the chat. And here we go. When n is equal to 0, I'm going to get just plain old 1. When n is equal to 1, I'm going to get plain old x. When x is equal to 2, I'm going to get x squared over 2 factorial. For 3, x cubed over 3 factorial. And the pattern is right there from there. By the way, I put squiggle equals where I have a polynomial that's cut off. E to the x is straight equal sign if I'm talking about theoretical infinity being able to actually exist. I write squiggle equal here because I cut the polynomial, and you need to understand that if you cut off the polynomial and don't have it going to infinity, it's squiggly equal. It is an approximation. On the p-test in the distant past, they used to take off points for not writing squiggly equal signs, so I still emphasize write squiggly equal signs. So that's e to the x. Sin x. Here we go. Okay, come on, pen. We're going to come up with a Maclaurin series for sin x. All right, sin x. What is the derivative of sin x? Cosine x. And what is the derivative of cosine x? Yay, negative sin x. And what's the derivative of negative sin x? Negative cosine x. And what's the derivative of negative cosine x? Sin x. Hey, that sounds familiar. We are back to the beginning, and pattern will continue. So now let's plug 0 in. All right, plugging in 0. Sine of 0 is dun, 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 dun. Sine of 0 is, checking chat, 0. What is the cosine of 0? 1. What is negative sine of 0? 0. What is negative cosine of 0? Negative 1. And then the pattern repeats. 0, 1, 0, negative 1. These are the numbers we are going to manually put into the Mclaren Series formula. So again, reminder of Mclaren Series formula. You need to write this down and think about it as many times as you can. Nth derivative at the center, which is 0 if it's Mclaren, divided by n factorial times x minus 0 to the n power. We're going to start with n equals 0. And then we have n equals 1, n equals 2, n equals 3, n equals 4. When I plug in n equals 0, this highlighted piece is replaced with 0, and should I bother with anything else? No. When n is equal to 1, this highlight gets replaced with a 1, and I have 1 over 1 factorial times x to the 1 power, so I'm getting x, just plain old x. When n equals 2, this highlighted part is 0 and times, who cares? When n is equal to 3, my highlighted nth derivative of 0 is -1. And then I finish the formula with my 3's divided by 3 factorial times x to the power of 3. And then I'm going to nicely write it as negative x cubed over 3 factorial. When n equals 4, how about we just don't bother? And what are we going to get with n equals 5? We're going to go back to positive 1, but with that n equals 5, I have over 5 factorial x to the 5th, which I can write more simply as x to the 5th divided by 5 factorial. Then I'm going to go over to 7. When n is 7, I will get negative x to the 7th. Okay. Technology. I don't even know what to say. All right. You can see that it decided it didn't like me anymore, and it got rid of the last bit that I did there. I guess that's called the internet saying, excuse me, I need a break. Okay, I'm back. All right. When n is equal to 7, I'm getting -1 over 7 factorial x to the 7th power. At this point, you should see the pattern. And I'm going to put this where you can see all the work we have done. And I'm now going to write the pattern that we have for the first few non-zero terms of sin x. Sin x, and I'm going to do squiggle equal because I need to end my polynomial. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And you should realize that the next term is going to be plus x to the 9th over 9 factorial. And then after that, minus x to the 11th over 11 factorial. Now, you need to make sure that you're following me with what I'm about to do. So write down what you're writing down, and then you're going to need to really listen carefully. Here we go. These values of n were the Mclaren's n values. When I come up with a formula for sin x and I use a sigma, I really don't want to have to use n equals 0, 2, 4, 6. I don't want to use the even ends. So what I'm going to do is I'm going to basically take all of this and be like, that doesn't matter. And I'm going to restructure what n is, where it starts, and how it goes. So those Maclaurin ends are not the ends I'm using right now, and you have to understand that. I'm going to let this term be what happens when n equals 0. And this is what comes out when n is 1, when n is 2, when n is 3, and so on. This will allow me to come up with a reasonable sigma formula. But again, the Maclaurin ends that we use to create these terms are not the ends we are using to create the formula for sin x as a Mclaren series. Based on these ends, do you think you see a formula? First of all, I need -1 to a power. The odd ends are getting the negatives. If the odd ends are getting the negatives, then -1 to the n power will cause all the negative ends to keep the -1 and all the even ends to square it away, or even exponent it away. The rest of it is x to the power of a number divided by that same exact number in a parentheses factorial. Do you think you have a pattern for those odd numbers? So it helps to be aware that if you need to create a bunch of odd numbers, you're going to start with a bunch of even numbers, 2n. And then from there, figure out 0 times 2 plus 1 gives me 1. 1 times 2 plus 1 gives me 3. 2 times 2 plus 1 gives me 5. Whoop, we're working. 2n plus 1. You must have the parentheses around the 2n plus 1. You must have the parentheses around that 2n plus 1. You need to know this formula, and you need to be familiar with the first few terms. Tomorrow, we will look at a way to find cosine from what we already found with sine and save us a little bit of time. Now, I want to point out to you some things that are going to help you with memorization. The first thing I'm going to do is remind you of something from long, long ago. Long ago, you were asked, is that function an even function, an odd function, or neither? Does that sound familiar? Even functions have y-axis symmetry. Odd functions have what's called origin symmetry, which means they go through the origin, and whatever happens with x when it is positive, the opposite signed y value goes with their opposite signed x's. So I'm going to try and draw it that way. When a function is even, if you go the same distance from 0, you get the same y value. If you have an odd function, when you go the same distance from 0 horizontally, you get opposite signed y values. If a function has neither even symmetry nor odd symmetry, that doesn't mean it has no symmetry. It does not have this specific type of symmetry. So I could draw a parabola, and a parabola has symmetry. You know that. I can draw it anywhere I like. But if I do not draw the vertex on the y-axis, it is considered neither. It's not an even function or an odd function, regardless of the fact that it does have symmetry. It's not the right kind. Now, if you write a polynomial and it's an even function, it might look like x to the fourth minus, let's go with 3x squared. And let's say maybe plus 8. A polynomial is even if all of its exponents are even, and let me technically say that when you have a constant, that's times x to the 0, and 0 is an even number. When you have a polynomial that is an odd function, it has only odd exponents, and it can't have a constant term because it's got to go through 0. So an example would be, let's do 2x to the 7th power minus x cubed plus 9x. As long as it has only odd exponents, it is an odd function. If it's got a mixture, I can't write anymore. It doesn't matter. I've got an odd, I've got an even. It is neither. For a polynomial to be an even function, it must have only even exponents. An odd has only odd exponents. And now I have one more question for you. What does sine look like when you graph it? What is the graph of sine? Sine goes through the origin. La 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 la. And if I go backward, you know what? I'd really like to be able to say that tune backward, but I can't. So la 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 la. There we go. Sine is an odd function. If I am centered at 0, an odd function's polynomial has to be odd. Let that help you to remember the formula for sine. I also want to point out to you, did you notice the similarity with e to the x? E to the x, if I write a first few terms, it's 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial. E to the x does not have an even or odd symmetry to it. Its polynomial takes on every single degreed term with the formula of x to the n over n factorial. Sin x takes the terms from e to the x that are odd and then does a back and forth negative sign. So I start with x and then minus x cubed over 3 factorial, and then plus x to the 5th over 5 factorial. So I get an alternating series where it goes directly from positive to negative, positive to negative, positive to negative. Da, 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 da. Let that help you in learning these two formulas.